So for each reduced voltage, you'll just get a graph like that. So then your load curve, regardless if it was an exponential or a linear or even something more constant, every time it'll just intersect at a different place. So each of those intersection points, you'll get a specific torque and a specific speed. So that's the more common way of doing it. Whereas if you increase the armature path resistance by putting let's say a variable resistor in the armature path, well, that'll happen then is if this one was your original graph at full voltage, you won't change the voltage, you'll just change that resistance value. That resistance value will have the effect of making this graph steeper. So remember, the more perfect the internal resistance was, the armature, if it had almost no internal resistance, then we end up with no volt times no IR drop across the armature. In that case, the back EMF would equal the supply voltage, and the thing would actually have a straight line graph, a horizontal graph. The speed would never change. But if we have a real resistance, we get a bit of a slope going. If you increase that value of resistance, then the slope becomes steeper. Again, that would mean instead of intersecting perhaps over here in one case, we intersect now over there in some other case, and it would get some speed reduction. But it's never going to be as good as getting the whole voltage curve shifting down. And for example, under those conditions, your maximum torque that you could get would be out here somewhere, whereas normally the maximum torque we could go right to the outside the screen here where it would intersect the line. So there's certain limitations for those methods. The other method is one of them which when you weaken the flux, that was your normal graph. When you weaken the flux, the graph ends up looking, this thing becomes twice as high if you halve it, for example, but the graph actually gets steeper as well. I'm trying to think what the reason was. Anyway, it depends where the load is. Sometimes you could intersect and you could actually be operating faster, but there are times if you have a high torque where you could actually end up operating slower, depending on which side of this point you intercept. But yeah, that's a bit of detail we don't really know. But basically, the field winding scenario, when you reduce the field, the speed actually goes up for the no load case. But reduced flux can also mean you need more amps to achieve a certain torque. That's right. So if you want a high torque, you've got to feed lots of amps through it, and then the graph drops off quite steeply. But you can actually get, even with a reduced field, you can actually get the thing slowing down in that region. But if you've got a load which allows, it allows it to run fairly close to no load speed, not that much torque, then you will get an increased speed when you reduce the flux in that field by putting a resistor in there. So yeah, have a look through those. But yeah, we can jump then into Worldy. So I gave you a link. Did you get that link? Okay. So at some point you might want to call that up. Now I wanted to sort of be able to draw like I normally do over this PDF, but I forgot last time that the version that I eventually found to edit over a PDF, I didn't have a pro version here at home. I wanted to do it like on an online version, not one that you could download. And I think that's what was slowing things up when we first logged on and I was having all those hitches. So I've shut that down. So for now, I'll just sort of highlight things with my mouse, hopefully, if you can see that a little bit. Okay, so if you jump straight to page 183, you'll get to the section on ideal transformers. So this book looks something like that, or a couple of copies in our library. That won't help most of you guys. Where's everybody stay? Mark, you were, was it Ben? Ben, you were talking about, you're in Invercargill, were you?
I'm in Benmore.
Were you, Mark?
Benmore.
Where's that?
North Otago.
Okay, so I'm only a year and a half living in New Zealand, so forgive me if I don't know all the areas. Because I think, Ben, you were far away, eh?
I'm in Greymouth on the west coast of the South Island.
Okay, that's a bit of a drive, bit of a swim as well. So anyway, the library won't help you. On that score, then it was you that had discussed the flight times.
Yeah, that's correct. Yeah, Mark and Cameron will be interested in that too.
Okay, because Ben had asked me on our block course days, we've got the Thursday and the Friday.
Yeah.
And he'd been saying, what can you book a flight? What time did you want to book a flight, Ben? It was quarter to 4 or something.
The 3:50 flight usually works well for us down in the South Island.
Yeah.
Right, because you're still going to get across and then drive and this and that. And I said I didn't think anybody would mind if we probably just go a little later on the Thursday if necessary, so we can finish a bit earlier on the Friday. If people want to get going a bit sooner, because most of you will have nothing specific to do on the Thursday night because you'll be just staying over, right?
Yeah.
So you won't mind going a touch later on the Thursday, like maybe till, I don't know, 5 or 6 or something. So we can end at 2:33, something like that on the, whatever will give you enough time to head down to the airport by the... Okay, so that should be okay with most people, I'd imagine?
Yeah, it's fine with me.
Okay, cool. Yeah, we just got a couple of tracks to get through, but we should have enough time. Okay, so Transformers, trying again.
How much would this book cost if we were to purchase it, do you know?
I have no idea. But we don't like bird. We're kind of half with Wildy and Bird, so you could get away maybe just with printing a couple of the chapters if you wanted to as well. I can find out. I can try and find out, but I know the library bought a couple of extra copies, but yeah, it doesn't help for the distance guys. So yeah, it doesn't help too much, but I don't really know, to be honest. But yeah, we don't need the whole book.
Would there be more content in this one on the DC machines? Like some of the stuff's not in there that's in the assortment. In Bird.
Armature Reaction is in here. This book in general is more detailed than Bird. So it gets a bit intense, in fact.
Oh, yeah. Because there's nothing about braking resistors either in Bird.
No. Yeah, I'm throwing you in the deep end with the braking resistor one. But basically, that thing is generating an EMF, and if you just apply a little bit of Ohm's law kind of thing, you should be able to figure out what's happening there. Give it a try. If you can get it, you can get it. If not, leave it out. If you get 90% instead of 100%, it's not that bad.
About 50.
But yeah, as the motor, as you flick that switch, the thing will still be spinning. When it spins, it still generates an EMF. That EMF will try and drive current through that armature circuit, which now includes resistors. So just by applying some basic Ohm's law scenario, you can, and I think I gave a relationship between current and torque as well. Yeah, see what you can do. Yeah, there might be something on that in this worldie. There's something, an armature reaction in there as well, but I'm sure you can find it on the net. But in general, he goes into a bit more detail than Bird. But the transformer section, although it's more detailed, I do find it more. Although it's more detailed, because it gives a clearer understanding, and it's more useful in terms of what we can do with those equivalent circuit that we're going to end up with. And also, we're going to use that equivalent circuit for induction machines as well. So some of the things that we discover in the transformer section we'll be kind of reusing in some of the future sections. So we spend a little bit of time on transformers, but at least the principles are applicable to some other parts of the work as well. Not too much to the synchronous, but at least to the induction. So yeah, Worldy is definitely a little bit higher up there. But from that point of view, probably a good book to have in the sense that it covers a lot of things. including power electronics, and well, that's probably not the newest book, so I'm not sure if there's some technology which it might not discuss. So you'd have to look at the edition dates. But yeah, pretty good book on the whole. So I can inquire about the cost. But for our purposes, you just need really the chapter on. Well, there's actually 2 on transformers we're going to do. One on ideal transformers, one on practical transformers. In fact, there's a 3rd one on transformers, which is more on 3-phase and other special transformers. So yeah, I guess that starts to add up. It's kind of 3 chapters there. And then it's a chapter on synchronous machines. And there's a little bit on single-phase AC, because we do Bird for AC, but that for 3-phase, he doesn't have anything on single-phase. So we jump back into Wildy. So yeah, there's a fair bit from Wildy. So yeah, especially if your company can buy it for you, then why not?
Good luck.
If. Okay, so let's get stuck in, and I'll leave some of this obviously for your reading skills, because you're getting pretty good at that, I'm sure. So as not to take too much of your time. And by the way, since I'm doing this from my home computer, I think it's going to possibly shut me off after about 40 minutes, and it's going to force us to restart the meeting. I think it only allows 40 minutes if you're not logged in as a professional user or something, which I would normally do if I was logged in on Wintech side. So if we get cut off, we can just sign in again. And I'm pretty sure that you can use the same. I might just go to the site and change the time to be slightly later, and then we can hit it again. I'm pretty sure you can use the same link. Right, I'll try and highlight the important things. Voltage induced in a coil when it links a variable flux. So I'm not going to go back to it, but you might remember from the Bird section where there was talk about the relationship between a voltage and a flux. You remember for induction, there was V equals N d flux by dt, I think it was. So for when flux is changing, collapsing or building, magnetic flux in a circuit, then any conductors which are basically perpendicular to that field or by means of or linked to that field like a coil, those inductors start to have a voltage induced in them. So a collapsing or building flux, d flux by dt. Sorry, I can't draw on there, of course. That d flux by dt gives you, it's a change, and that will induce a voltage. So we'll always have that the flux is, basically the flux is peaking over there while the voltage is reaching 0. And likewise, when the flux is 0, then the voltage is the max, because when the flux is 0, that's where it's going through its steepest part of rate of change. Sine wave, the steepest rate of change is at the crossing, and then the smallest rate of change, of course, it falls to 0 as it flattens off before it goes down again. So where there's no change, we've got a tangent there, horizontal, we get a 0 EMF induced in the coil. And when there's a steep change in flux with respect to time, then we get a high peak. Or if the flux is changing negatively over here, we get the low peak. All right, so this formula comes out of that d flux by dt story. So all they're saying here is that there's a max flux for that whole magnetic circuit that's achieved. Is proportional to the number of turns, and it is proportional to the frequency as well. Okay, where does that little lot come from? The exact value there, the 2 pi business comes from, and with inductance, we have 2 pi f gives us a radians per second. And I'm sure you'll remember your formulas for inductance. It's based on a sine wave, so radians per second becomes important in there. So in that 4.44 is a 2 pi somewhere to convert a frequency to a radians per second, omega. And then also there's a root 2 because we're looking at this as a sort of an RMS value, a continuous value, whereas this is a peak value. Okay, so this is giving us a relationship between an RMS voltage and a peak flux, not an RMS flux. The reason, as they explain here, and we'll read a little bit further down, the reason that they want to use the peak is because if you're designing the transformer, that peak mustn't be in the saturation region. It must be before it saturates. So one actually wants to be aware of what that peak value is because, of course, it's significantly higher than the RMS value. So although they don't say RMS here, we're dealing with a phasor, things changing with time, sine wave essentially. So that is an RMS value, but that one is not. All right, so that's just the formula. That'll be in the formula sheet. The derivation of that I'm not too concerned with, but basically it comes down to those fundamental principles relating the rate of change of flux and the voltage induced. It will change a bit if your frequency changes, but generally with transformers we're dealing with fixed frequencies most of the time for power stuff anyway, 50 hertz. So the F is not going to change in our formulas, generally speaking. What else is important? Okay, resistance of the coil. Typically the coil resistance is a lot smaller than the reactance. So we're dealing with the sine wave thing. So as soon as we've got AC in the mix, we mustn't consider just resistance. We need to know impedance because of the inductance, because it's being a coil, and not just a coil, in fact, but a coil with a nice magnetic core, which makes its inductance even higher. But assuming that it is negligible resistance, then our inductance, what is it, Z equals R plus JX. If the R term is small, then we can just focus on the X term. And this formula is just looking at magnitude. So I'm not looking at the phase shift, just looking at magnitude here. Basically, we're just saying that's equivalent to Ohm's law, right? E equals I, V equals IR. But we're not dealing with R, we're dealing with Z. But not Z, we're dealing with a subset of Z. The R happens to be 0, and the X component is all that matters. Okay, so basically because it's an inductor, we have really reactance only, and we'll end up with a current, a magnetizing current, which ends up 90 degrees behind E, where E is the applied voltage that they're putting on this thing. So they've put E across the terminals there, and they've ended up with I. So it's a magnetizing current. There it is there. Can you see all right if I'm just doing that with my mouse? I can't draw on this particular screen. Can you see my mouse moving there? No movement.
No, I can't see your mouse.
Mark and Cameron, I can't. Your sound is off.
I can see a wee cross.
Yeah.
Oh, yeah, there it is. There it is.
There.
Gotcha.
Okay. It sometimes changes from the arrow to the cross. The cross.
Oh, I see it on the right hand side there. Yeah.
So if I come to the side here, if I want to show something, and then I go across.
Yeah.
You probably can see it all right. Okay. Yeah. Good enough for today. If I need to sketch something, I'll go to that OneNote page so I can draw there. I just can't draw over this PDF. All right, so I'll go to the right and then I'll create it to make it easier to see. All right, so we're getting a magnetizing current produced by voltage. So as a vector, in an inductor, we know we'll always have our voltage exactly 90 degrees ahead of our current. So if we choose the voltage as the phasor, then the magnetizing current will be perpendicular to that. I mean, it's 90 degrees, so it's phase lag of 90. It's an inductor. It's in the same orientation as the flux, because what produces a flux? It's the amp turns. Flux is produced by amp turns. So as amps run in your circuit, so flux is produced in your circuit. So the magnetizing current that produces that flux and the flux itself are the same. They're 90 degrees compared to the, we take this as the reference, that's the supply voltage. Okay. The distinguishing here between EG being the, sort of call it the generator voltage, if you like, the supply voltage, and E being the voltage induced across the terminals, but they are the same. We've just got two wires here. Those 2 points and those 2 points are the same, but they do explain why they differentiate, why they're distinguishing between those two, but it's not really important. Right, so the better the transformer, effectively, the less current you need to create a nice big flux. So a very good, almost ideal transformer, this vector here, this IM, will start to shrink towards 0 and still allow you to have a nice voltage produced. So a very good transformer won't actually absorb much current for the magnetizing effect. We're not looking at the current drawn due to the load. We're just looking at the current. In this case, it's actually just for a single coil. We haven't even put two coils together yet, but the principles are the same. Let's actually jump there to where we've got the two together. Some terms which might become useful later on is we talk about a mutual flux, which is flux which is seen by both. The magnetic field lines pass through both coils. So that's a coil there, the primary side. That's your secondary coil. Primary, any side that is receiving power from some source is going to be your primary side. And this one would be where we're putting a resistor or something, a motor, whatever it might be, between those two terminals. So that's where we're delivering electrical power to. That'll automatically be called the secondary side, regardless of whether we're putting voltage step up or step down. Primary would be the power input side from a voltage source, typically, and the secondary would be the electrical output side. Okay, so we get the mutual flux and then we get leakage flux. Now, if we put a metal path along here for the magnetic field lines to run through, then mostly we'll have, or most of the flux will be mutual flux. It'll be seen by both of them. And you'll have a very small amount of leakage flux that only links one turn and doesn't actually come into the other one. But an ideal transformer, we will have perfect linking. So all the flux that this guy produces will also pass through that guy. Okay, let's talk about the property, the polarity marks while we're about it, just because it's here. That's the way Wildy does it. He just has two black dots. Later, though, he does tend to use an H1 and X1 for input sides and H1 and H2 for inputs and X1 and X2 for the secondary side. So we'll see that later. But for now, the dots just mean that these two have the same polarity. Of course, this thing's polarity, it's always swinging. It's AC, so at one instance in time, this point is positive compared to this one. 20 milliseconds or 10 milliseconds later, whatever it is, 20, eh? No, 10, half a sine wave. This one will be more negative here compared to this one. So we do have fluctuation happening all the time over here. But what these polarity means, what the polarity marking means is that at a particular instant when this one happens to be positive compared to this one here then will also be positive compared to this one. So if that's positive at an instant, so is that one. If this one happens to be negative at an instant, when this voltage has been reversed over here, then that one will also be negative. And then also, if any current is coming in here, by definition, with this polarity marking over here, current will be getting sucked out of here. So current coming in on the primary side, it sort of comes in on the primary so that it can feed out of the secondary. So you'll imagine at some point we're going to be connecting loads, resistors across here. If that's positive while that's positive, we're going to have positive here and negative there. That's going to draw current this way. But that current will come from current getting fed in. Because remember, although that's positive and that's negative there, we won't have current going negative to positive that way, because that would happen if this was a resistor. But this is a voltage source. And the voltage source, it's able to force current to not go from positive to negative. It forces current to go from a negative side of a voltage source to a positive. The whole thing about current flowing from a high to a low, it's really only when it's losing energy as it goes through a resistor. If you're putting it through a battery, it's automatically going from a low side negative to a high side positive. Then in the rest of the circuit, it's dropping until it gets back to the zero side. So yeah, current's being forced into it here at a given instant, and current will be getting forced out of it here and through the load. And then 10 milliseconds later, current will be getting sucked out of here, and current will be getting reversed in this resistor and getting sucked in over here. So this thing works as if it's a circuit. Current coming this way will go through the circuit this way. Current coming this way will go back through there. And that's just oscillating like that all the time. And of course, the flux here is also changing polarity all the time. Typically, they'll represent a transformer by just a box like this, and with the two polarity markings, and then a letter called A, which indicates the turns ratio. I'll get to that in a minute. Okay, so a bit of reading to do here. Important things. Okay, here they're showing you they could draw it like this. If that's a dot and that's the dot, then if this one's positive at the same instant, that one will be positive. And if current's getting fed in here, then current will be getting sucked out of there. Regardless whether they draw the dot on the top or the bottom. Whichever one has the dot means the polarity will be the same as that one at a particular instance. And when current goes in here, current will be going out here. We often do show a current direction in these things, even though it's always changing. It's just that it gives you some reference. So on a phasor diagram, when you see a voltage at a certain time t equals 0, and it crosses that zero axis, at that instance you have a vector a certain way, a voltage a certain way, a current a certain way, other currents relative to that, just so we can see at an instant how the things relate to each other. But yes, 10 milliseconds later, everything changes. Okay, let's see. Okay, there's two coils, the primary and the secondary. Both of them are governed by this relationship where we relate a changing flux to a voltage that's produced, a changing flux to a voltage that's produced, induced. So because the flux is the same in both of them, whatever the primary causes, in other words, causes a magnetism that the secondary sees, and whatever the secondary causes, the primary sees, because that mutual flux is linking both sides, it means that you can set these two equations equal to each other. The two fluxes are the same, they're mutual, which means that you can end up that if you solve for it, once you've taken flux, you write flux by itself, you write that flux by itself, set them equal together, and the 4.44 term will drop out, will cancel, the F term will cancel, and you'll get left with there's an invisible line between those two, but it just says the ratio of the voltages is the same as the ratio of the turns. So in other words, for a given amount of flux that's changing per unit time, if you have more turns, more coils, that flux is seen to collapse and grow in, on, through, whatever, it will induce more voltage as an effect. So that's the important thing here. We all know this already, I'm sure. primary voltage proportional to primary turns, secondary voltage proportional to secondary turns. Easy as that. By definition, that ratio of primary to secondary is called A. A could be a number greater than 1. Would A be greater for a step up or step down?
So for a step up, going from primary to secondary, you'd have more windings on the secondary to go step up, wouldn't you? So A would be smaller than 1.
Yeah, that's right. That's right. Secondary would have more windings than primary, you're right. So A would be a number less than 1. That's right. Just trying to think about something. Yes, step. Hang on a minute. Yeah, that's right. Okay. What else do we need? Okay, there's our ideal transformer. Let's see what's happening with our vector diagram now. Okay, so the vector diagram we looked at previously was, if I go back to this one, in the same way they started off showing for a single coil, then they showed it for a transformer. The primary voltage, both primary side and secondary side, and the applied voltage, they all end up exactly in phase. This is under ideal transformer and no load conditions. The magnetizing current ends up exactly perpendicular because it's an inductor, so we've got that 90 degrees phase shift, and it's very small because it just has to create a little bit of flux over here. We've got a very easy magnetic path. Low reluctance is the term. So the ideal transformer, this thing will approach 0, and we'll get a nice flux produced. We'll get voltages induced. They're in phase because the flux, as the flux builds over here, so it's also building over there. When it collapses here, it collapses there. So the voltage is induced either side or also in phase with each other, but they're 90 degrees out of phase with the current. Then if we put a load across the end here, then we don't just have this little bit of current that is being used on the primary side to create the magnet, to create the magnetism, the flux. Then we actually have extra current which is flowing because of the load. And basically it stands to reason any current that's getting sucked out here has got to come from somewhere, so it causes more current to get sucked in on this side. But not exactly, it's proportional, or it's inversely proportional to the turns ratio. So let's come back down here. So here we're talking about the current ratio. That is just saying that the secondary current is related to the secondary voltage divided by the secondary impedance. So that's the load impedance. So on the right-hand side now we've got a load between the terminals of the transformer. That load primarily actually determines, well, especially for the ideal transformer, that load and only that load determines how much current flows in the secondary. Okay, but when that current flows, so it'll be a certain phase lag between the secondary voltage, which is in phase with the primary. That phase lag there will be dictated purely by the phase angle, the impedance triangle, that one. The tan theta thing relating the reactance and the resistance, that phase angle purely will relate how far back this current is compared to the voltage on the secondary side. But because it's a perfect transformer, it actually requires that the phase shift for the primary side will end up being the same. What happens here is that they explain it down here. When we have amp turns created by the primary coil, immediately there's amp turns that have to be created by the secondary coil, so that you have basically sum of MMFs is 0 around the magnetic loop. So as current pushes in on one side, current immediately gets forced onto the other side. So basically, by forcing ourselves a current to flow over here, instantaneously, as a current gets sucked out over here, the current has to get sucked in over there. How much gets sucked out over here? Well, it's purely dependent on the size of that load. The voltage here is dependent purely on the size of that voltage there and the number of turns ratio, the turns ratio. And once we've established that voltage, it's purely the size of this load that determines how much current gets sucked out of here. Would you call a low load a high resistance, or rather impedance, or a low impedance? Cameron and Mark, don't forget your mute is on.
So a high impedance load would be a low load, wouldn't it?
Yeah, because it wouldn't draw much current.
Yeah.
Okay, and pretty much in a real transformer, we'll see that this voltage here dips a little bit, but in the ideal one, that voltage is completely fixed because it's just equal to the primary one times the turns ratio, so it's fixed. So if you put a smaller impedance here, and you go I because V over Z, you'll draw more current, and the voltage is the same, so power is product of volts times amps. So the V is the same, the I is going up as the resistance comes down, so a small resistor is actually a large load. So if you keep connecting light bulbs in parallel over here, you're actually making a smaller resistor, and you're getting more and more current sucked in over here. And whatever current gets sucked in over here, we get this effect where as current happens in one side of the coil, it must instantaneously happen on the other side, so that the sum of the magnetic MMFs around the circuit is zero. Let's call it the bucking effect over here, down the bottom here somewhere. But it's the product here, the product of amp turns it produces an EMF is equal to the other product of amp turns. So the primary amp turns equals the secondary amp turns. So of course, the relation of the one current relative to the other is also related to the turns ratio. You can rearrange that formula, obviously, divide the I's, divide the N's. We end up with that. And here you can see that the currents are related to the inverse, obviously, of the turns ratio. So it's 1 over, there's an invisible dash over, invisible line there, by the way. I don't know why this PDF is not the clearest, but yeah, the inverse of the turns ratio to get the current. Okay, so far so good. So there's the two currents, one in the primary, the one in the secondary. They're in phase. As one gets caused, the other one gets caused, but one is smaller than the other because the turns ratio is not the same. Meanwhile, the flux itself is still down here because the flux is not produced by this current. The flux is produced purely by that little bit of magnetizing current, which we'll see later is a little bit of an extra bit of current that flows in here. But it approaches zero. It's a little bit of extra current. It's not related to the current that's getting, there's kind of two components. There's current that flows here because we're sucking current through the load, according to this formula, this one. But there's also current that flows in here to set up that magnetization, to get that alternating flux going. Even when we've got no current, if you've got an open circuit here, no current there, then in theory we shouldn't have any current getting pulled into the input side either. There's no power output if there's no current there, right? We should have no power input either. But there's a little bit of a bleed of current for that IM, they call it, that magnetizing current, to actually create the oscillating flux. But it's a very small amount compared to the load side of things. So there is a little bit of current required, but in the perfect ideal transformer, that current approaches 0. In other words, it needs a very tiny amount of current if you've got a very easy magnetic path, very, very low reluctance. But in reality, you've got to take a significant amount of current to actually get some flux in that magnetic circuit. But it's still only a few percent compared to the current that flows under full load. Right, let's keep pushing. If this thing cuts out at some point, we'll just know to dial in again. Okay, you can have a look through all of that stuff, They show this as being at any angle over here, although of course it would be impossible to get an angle that's larger than 90. But anyway, it's just arbitrary. The two currents are the same. And that angle is dictated purely by the size of and the nature of the load. Okay. Right, so here's the way that they show it. They just normally put a little T in a box for a transformer, and they show a number A, meaning N1 over N2, N1 being the primary turns, N2 being the secondary. So for example, like you said, if A is a number greater than 1, it means N1 is higher than N2. It means you've got a big voltage coming in and a small voltage coming out. So that's a step down. The step up and step down is always in terms of voltage. Of course, in terms of current, stepping down a voltage, we know will actually step the current up. But the definition, step up and step down, is purely based on voltage. Because the current can be anything, depending on the load. Okay, little explanation here about an impedance ratio. If we can talk about, if I have a real impedance over here, if I take the ratio of what's Ohm's law, V equals IR, so R is V over I, or Z is V over I. If we take a ratio of a voltage and a current through a device, we'll get the impedance of it. Huh? E equals RZ. Okay. So by simply knowing a ratio of a voltage to a current, we can know an impedance. But we can also talk about an impedance as seen by the supplier. So if you had a normal circuit, you'd have a supply voltage here feeding some kind of a load voltage. And if the supplier knew that it had a certain voltage between its terminals and it saw a certain current, it would then know what that impedance is. It would take the ratio of its current voltage to its current, and it would know what that impedance is. So as far as the source is concerned, it doesn't know that there's a transformer in the way. It just sees a certain current being produced when it has a certain voltage. So as far as the source is concerned, which is on the primary side, we can talk about referring a voltage, an impedance on the secondary. We can talk about referring it to the primary. Then we're talking about what that resistance will look like on the primary side when it gets fed by the power source, the actual voltage source of your circuit. So if you work this out, because of these various ratios, you end up with, if you take a real load from the secondary side and you want to draw an equivalent circuit where you take the transformer away and you just draw a simple circuit like that, if we multiply that load by A squared, where A is the turns ratio squared, we'll come up with an equivalent impedance, which is what the supplier will think that that impedance has in terms of the current that gets drawn through it relative to the amount of voltage that the supplier is putting out. And that supply voltage is seen by this theoretical load impedance referred to the primary. That's the term they use, referred to the primary. So this is a very simple version of an equivalent circuit where we can take this item and we can shift it across to the left-hand side and model it as if it was here on the left-hand side. But we multiply it by A squared, okay, to make everything work, because we are dealing with changes in the voltages and the currents. Very important aspect this. We're going to show how we're going to use this for the for the ideal transformers. We're going to use the similar thing. It gets a little more complicated, but we're going to do the same trick for the practical or real transformers. And that's to do with this impedance shifting. And this is going to enable us to create an equivalent circuit for a transformer where we have a circuit that just has supply voltage and it has the load impedance in it, or various parameters, but it doesn't have a transformer in it. The transformer gets disappeared. So let's see what they were on about here. So there's a real circuit. It's an ideal transformer. It's shown as a turns ratio and a T for transformer. In this particular case, we've got some kind of a load device on the input side and 3 on the secondary side. What they want to show us here is that we can move these things from the secondary side. We can jump them over and replace them on the primary side as long as we multiply. This is large slightly. So they've taken that one and they've shifted it over and they've put it here. And they reckon they're entitled to do that as long as they multiply the size of that impedance. So that is, as long as they multiply it by A squared, where A squared is that turns ratio, the A is the turns ratio. All right, so that thing is now gone from that side to this side. They do the same thing for this one. They shifted across from there to there, but in the process, there it goes. They've just multiplied its impedance by the turns ratio. Same thing, they moved this one to this one. There it goes over there. It was over here. Now it's gone. And it's reappeared over here. Again, they've multiplied it by A squared. So now you have a thing where the load is gone here. There's nothing over here. So there's no current. It's open circuit there. If you've got open currents, if you've got open circuit over there, so no current can get sucked out here, it means no current can get sucked in there either on the primary side, right? Ideal transformer, if you don't suck any secondary current out, the primary current is inversely proportional to the turns ratio, but no current on the secondary, it means you don't suck anything in here either. So this whole thing here is a dead end. That means we can actually show it like this. So the dead end, we've taken it away. It was sitting over here. So it's gone. So now each and every load has been redrawn as if it was seen by this thing to be on the primary side. And the transformer has now disappeared altogether. And now we're in a position where you can analyze this. You could analyze this to find what currents flow and what voltages are produced across these different components by the normal rules of single phase circuits, where we've got known impedances with known resistances and reactances, and you'll have like these two guys are in series, and the combination of these two guys is in parallel with this one, and this whole combination here is in series with this one. And so you could do an analysis on each and every current and voltage in here. What they explain though is that when we take something from one side and we shift it over, like, sorry, let's take this one. We take this from this side. Here it's easy to see. What voltage would this thing have seen? It would have seen the secondary voltage, right? Between those two terminals. When we make the shift, suddenly it sees actually the voltage that would have been seen here on the primary side. And we know that that voltage is different by the turns ratio, A. So in the equivalent circuits analysis, we must bear in mind that if we came along with a voltmeter and we tried to probe across here to see what voltage actually is, to see what voltage the voltmeter would measure there in theory, it would measure A times higher than what it would have measured if you'd put the same voltmeter across here. Okay, quite a key principle this. Because the voltages on primary secondary side are related with this turns ratio business, it means that if you measured a voltage here, and you take that same thing and you move it to the other side here, yes, you must change its impedance so that you get an equivalence, but the voltage that you measure there won't be the same as the voltage you measure there. It'll be A times higher. So when we come to work out the numbers in these circuits and solve for the numbers, for example, we can come along like here and we can try and work out what voltage we would have here according to our normal parallel and series analysis of a circuit. And once we've worked out that voltage that appears here on the equivalent circuit, we could say that voltage is equal to A times what the voltage will actually be when it's sitting on the secondary side like it was. So we analyze it like this, as if everything's on the primary and the transformer is gone. We solve for a voltage over there. Once we found that voltage, we realize that that voltage is equal to A times the actual E4 that would appear if it was actually sitting on the secondary, which in reality it is. So if you solve for this and you get a number of 100 over here, and the turns ratio is 2, we'd say 100 is equal to 2 times that, and you'd end up with 50 volts here. Make sense? We'll see a worked example shortly where they do that. Okay. Whatever voltage they measure here, that number is equal to A times E4, where E4 is the actual voltage on the secondary side. Currents, on the other hand, in the same way as the voltage across this is A times higher, the current through it is A times lower. So there's a slash there. It's R4 divided by A. So every time you, again, for this equivalence business, every time you move an impedance from a secondary to a primary, you need to bear in mind that if you go and solve now for a current through this one based on this equivalent circuit, and you find a current, the current that you've just found is actually not equal to this current, it's equal to that current divided by A. So to solve for the actual current here, you must take whatever current you found here and you must multiply it by A because you actually want that one. So this current vector here is equal to I4 over A, where I4 is what you actually are wanting. It's the real current in the real secondary of the real transformer when the load's on the secondary side like this. All right, so we'll use this equivalent circuit business to be able to analyze easily for currents and voltages, but then we must remember that the actual voltages and currents concerned, we must bear in mind this A factor there and this A factor there. And this relationship with the I over A and the AE business is the same whether we're moving a thing that was like parallel, like this one going here, it stays parallel, or whether we're moving this one, which then went to here. It doesn't matter. The principle is always the same. Where you see a voltage across a device, that on the equivalent circuit, that's equal to A times the voltage on the real circuit. If you see a current through here, that's equal to that current divided by the turns ratio A. Okay, so that's, you can also take things on the primary side and move them to the secondary side. That's less common, but you must just do the kind of the reverse of what you were doing. And they say you can even take a voltage source and you can move the voltage source onto the, let's zoom out here a little bit. You can even take a voltage source and move it over to the right-hand side. Now everything's on the secondary. So you can take that impedance. This time you must take it and you must divide it by an A squared there. The impedance conversion has an A squared in it. The current and voltage, one has a times A, one has a divided by A. So you can analyze this thing now. We can get rid of this transformer because there's no current going in here. It's a dead end there. It's a dead end there. So we can block out this whole thing and have an equivalent circuit where we just analyze this part if you wanted to. You could say we can cut this off. We could say we just have a circuit like that. And that would give you the same, you could do the analysis like that, but again, when you measure the various currents and things, if you want to infer what's actually happening on this side, you must, again, work backwards through these funny ratios. Okay, so where does that leave us? It leaves you having a little look through that one yourself. All of these things, there'll be a similar procedure. Take each impedance and move it. So that one moves, it stays a capacitor. This one stays a resistor. Once they've moved, you can now add them together. We can add that resistor, and get a combined R. We can group that with this X, XC for capacitor. And you can do, you guys obviously are familiar with the complex numbers and the polar format of impedance and all those kind of things, the angle and the J and all that stuff. So as usual, once you've moved everything over and it's all on the same side and you've gotten rid of the transformer completely, now you can analyze these things and solve, group the R's together, get an R value. Take the X, combine that into a Z, then you'll do an I equals an E divided by Z. You can get a current in this thing. Once you've got a current in this thing, you can get this voltage. How? A certain current times a certain resistance will give you a certain voltage. So whatever you measure there, it's related to this one. It's not the same though, because it will be A times higher. It's A times higher. So you're going to divide by A to get back to what it will actually be over here. So when you solve for it here, you're solving it in the equivalent circuit. But then you actually have to go back and work out what it will actually be in the real circuit. Okay, so that was quick. Ideal transformer is sorted, which means we can just touch on some of the things of the real transformers, and then we can carry on with it next week. So we're doing pretty well for time. Okay, let me try and highlight the important parts. In the real transformer, we've got we don't have a perfectly permeable core. In other words, we can't take tiny current to get a nice flux going because it's a real iron core. So that's an imperfection. We will have some resistance in that winding, which causes some heat losses. So there's an Rm, and so that's the iron losses. Well, there's copper losses as well, which is to do with the coil, the resistance of the coil. We'll get to that one later. Firstly, we're looking at the production of this magnetizing current. To produce that magnetizing current, you need some current because the iron is not infinitely permeable. Also, eddy currents will be produced, you know, when voltages produce stray, changing fluxes produce voltages which produce stray amounts of currents running in circles basically inside the metal, doing nothing but producing heat. Yep. So we'll represent that as this R, and we also have hysteresis losses. Remember that hysteresis curve when you put current into the magnet and you take the current out again, the magnetism doesn't come back down the same curve. There's a bit of a power loss there due to that hysteresis band. So all of those things together produce, we can symbolize it as two symbols, an R for, it's a magnet, it's an X, a magnetizing reactance, there it is there, and an R term which represents the Like if you did R squared R on this thing here, you would get the heat given off due to those energy losses in that core. So there we've got a couple of terms. The IF is the small current drawn to furnish the losses of the resistance, of the resistor representing the ion losses. Then we've got the IM, which is the portion that represents the magnetizing amount that's required. End of the day, and we'll call this the exciting current. It's the combination of this IM bit and the IF bit. And it's currents which are required regardless of whether current is being drawn here on the secondary or not. So we're aiming towards an equivalent circuit for a whole transformer. And what we're looking at here is just the primary side at the moment. At this point in time, the secondary over here is open circuited. No current is flowing here. That means no current would flow here either, right? Because to get current sucked in here, we must get current sucked out there. If this is a dead end, no current's flowing here. But there is current flowing back and forth in the primary side through these parameters represented as X and R. And those are the parameters that are there for the setting up of this alternating flux. So this would be the no load scenario. No load meaning we're not supplying any external resistor on the secondary side, but we still do have a bit of power wastage. There is some current that gets pulled from the supplier. Some is not wasted though. Some goes to, for an inductor, the power is not wasted. An inductor, the energy gets stored in the inductor in the magnetic field, and then it collapses again and gives it back, stores it and gives it back. So this guy takes energy from the power supply and feeds it back again. So he doesn't actually waste anything. This guy though does. Those hysteresis losses and eddy current losses end up as heat in the ion. We will see later. This guy does cause a little bit of a secondary effect in terms of power loss because there's another resistor element coming in our circuit over here due to another effect that we're going to look at. And so to get the current going through here, it's got to go through a resistor first. So all the extra current that flows through here goes through a resistor. So you get a bit of extra R squared loss in that resistor that's coming, because of this extra current getting pulled through here. But in through here itself, it's just storing and giving it back, storing and giving it back. But this side is wasting real power. This side is using reactive power from the source. This side is using real power. When I say side, I mean the side of this parallel combination. But this all represents what's happening in the ion. It's happening in the actual magnet part of the transformer. Where does this come from? Can you see what that formula is about? That's V equals R squared R. Sorry, P. No, sorry, that's P equals, we've got P equals VI, we've got P equals R squared R, and we've got P is V squared over R. Remember those? But of course, it's not V squared over R, it's V squared over Z. But in this case, if you're looking at the R portion, that would be for actually apparent power, but we're looking for real power, so we're going to have the R component. This one's the same thing, but now it's apparent power is V squared over X instead of V squared over R. If you wanted to have the capital S here, then we would say E squared over Z, where Z would be the combined effect of those two things. We're entitled to do this. We don't have to use the currents. We should use the voltage in both cases. Why? Because the voltage is seen by both of them. This guy sees the full primary side voltage, E1. There it is there. It appears across this resistor. The other guy also sees E1. We can't use the current over here in these formulas because some current gets stolen by this guy and some current gets stolen by this guy. And we don't know how much each of those is. So these formulas we're using a voltage and the resistance. These are the same type of formula, but the one is real power and the other one is reactive power. Okay. What does that do? That means you've got some current required there for the magnetizing side of things. You've got some current required here for the power, the real power loss, hysteresis and eddy currents kind of things. And because now you've got an R and an X together, we're going to get a current which is no longer exactly 90 degrees behind. There's a component that's going to be in phase because the resistor, when this voltage goes up here, the resistor current goes up instantaneously, whereas an inductor, if the voltage goes up, the current starts to build. You know what I mean? So this thing now gets pulled from the perpendicular only. You get a bit of component this way, so it starts to have a little bit of a less than 90 degrees effect. Okay, I'm going to jump a little bit and I'm going to leave you with some thoughts to look at home. You can look at the power, that's the parent power. You know how to get from a parent power to a real power to get the Q portion. So you can look through that one, you can look through that one. And now we want to see the coupling side of things, not just the core side of things. Looks a bit scary. All they're trying to show you here is that we've got a mutual flux and you've got portions which are not linked, they're not mutual. The overall effect of all of those things is that we actually can represent these as another, we can represent it as another portion of a coil over here which is producing not linked flux and one that is producing linked flux and one that's again not producing linked flux. So this is the part that is linked or mutually, it's mutual flux, and this is what we call the leakage flux. And in a good transformer, this portion and this portion should be very small. Most of the flux produced by the coil 1 will actually be seen by coil 2 because it all tends to stick nicely inside this magnetic core. But there is a little bit that leaks. Bottom line at the end of the day is that they can represent this leakage here by these two parameters there. Simply a resistor in series with a reactance. Let's see if they explain what each of those two terms, same thing here. This leakage over here, they're represented by a reactance in series with a resistance. If you put a voltmeter across those 2 points there, it's what you would feel here. This guy effectively stealing some of the voltage and only leaving a slightly smaller bit for this load. Okay, a little hard to visualize what this all means, but let's check the terms here. This is a standard circuit that we're heading for now. You'll see these terms on the left-hand primary side. We'll see the same terms on the other side, and we'll see an ideal transformer in between. But we will also mix this diagram with, we'll mix it with this one, where these things weren't in series, these ones are in parallel, but we'll get to it in a minute. So we call the X leakage reactances. There's a 1 and a 2 for the primary and secondary leakage reactances. And we call the R's The M's are for the core, these R's are for the leakage. I'm trying to see the term that they want to, the term that we want to call it. Sorry, just going to find it quickly. The X is the leakage reactance, and the R is to do with the resistance of the winding, I'm sure. Yeah, okay, I'll have to just check, but the R is to do with the resistance of the winding, and the X is to do with that flux leakage. So to actually find these things, it has to normally be done by experimentation. We'll do some tests in our labs when you guys come for the block course, where we actually see the phase shift that we get, and we can deduce how much is inductance and how much is resistance and how much is real power, etc., etc. But key thing for our purposes is that, yeah, that one there represents the resistance of the winding. That represents the leakage flux. That represents the secondary side resistance of the winding, and that one represents the secondary side leakage flux. Those would be known as the copper losses because they're to do with the winding, whereas those other two terms that we saw, which were in parallel, are known as the iron loss or the core loss, because it's to do with the magnetization side of things.
Yeah.
All right, so end of the day, that's the most complicated diagram you'll see in the transformers chapter. And it's now just got all the parameters together. We've got the primary side winding resistance, we've got the primary side leakage reactance, we've got the XM for the core, we've got the power losses produced here by eddy currents and hysteresis losses. So those, as you can see, are in parallel with an ideal transformer. And on the secondary side, we've got, again, the flux leakage reactance term and a winding resistance term. And here's the load. So the transformer is everything inside this box from, that's the terminals onto the transformers there, transformer, and those two are the terminals at the end of the transformer. The transformer is everything in that box. But inside there are these various circuit parameters, and an ideal transformer sits inside there because it's a box with a T and a turns ratio. Okay, so that's the equivalent circuit. We've got these various components. We know what to do with them mathematically because they're conventional components. We've got a turns ratio, and the next step will be that we will take these things that occur on the secondary side and we will move them across to the primary side. How do we do that? We multiply each of them by that A squared term.
A squared.
So we'll take each one, we'll take A squared times this, we'll move them across. We'll take A squared times that, move it across. A squared times this one. This is the load. It's not the transformer. This is outside the transformer. That's the resistor or whatever impedance you put there, that you've got choice of what you put there. This is all in the black box inside the transformer. You can't see it. But we'll take the load as well, times A squared, move it to this side. End of the day, we'll then do this next time where we start to look, if I page down, we start to look at using a equivalent circuit. Sorry, I'm jumping a bit. As you can see, we move all of those things over until we've got everything on the primary side only. Then we're going to group together the R terms and the X terms and shrink certain terms down into one impedance representing all the internal losses of the transformer and another one representing the load. And then we can actually analyze how much current flows here, because you can analyze the circuit as these things in series. And at the end, we can convert back again to the voltages that the load will see versus the voltages that you'll see across these internal. So it's a little bit like a battery with an internal resistance. We'll have an internal impedance here and then a load. And the internal impedance will steal some volts so that the load won't see everything. It'll see a portion. Okay, but that'll be for next time. Yes, have a read through this portion on the types of, the transformer, the manufacturing methods, and the types of cooling. There's always cooling for these things because you've got R squared R heat losses effectively in the iron and the windings as well. So you have to get rid of that heat somehow. So it can be air cooled, water cooled, forced air cooled, natural cooled, natural convection, whatever. The different types, obviously the bigger transformers, typically you tend to force the air through there, and you would tend to have, when I say water cooled, it's actually normally oil, liquid cooled. But there's a radiator and a fan blowing over the radiator typically. They use the lamination so that you don't have too much eddy currents. They design the thing to operate here just at the edge of the saturation region. If you go up into this region over here, suddenly you get currents that are produced very easily because the magnetic circuit doesn't need to kind of absorb that current to make more magnetism because it can't make any more magnetism. So you get some current spikes and things if you operate out here somewhere. So we're trying to avoid that. But we'll pick it up next time then. Okay, transformer taps, I'm sure you know a bit about that as well. We can talk about those next time as well. That just gives us a way of changing our ratios so that we're not exactly stuck. If we want to tweak the ratio on the output, we can connect between this point and either that point or that point or that point or that point, where each of those points sees slightly less turns. So that the turns ratio between output and input will be a little bit different. So if this voltage dips here a little bit compared to what you want, you can just select a smaller tap so that this thing sees a bigger ratio here, and this one will actually end up boosting it on the secondary side. So you can make these adjustments. And here they show you, okay, the H1s and the X1s. We'll come to that next time. Yeah, have a look through those terminal markings, polarity tests. The H's are what they use for the primary side and the X's for the secondary side. So a 1 and a 1 correlate the same as those polarity markings. And a 2 and a 2 correlate. So an H and an H is both on the primary, X and X is on the secondary. And if you see current coming into an H1 terminal, the current will come out of the X1 terminal. If the H1 terminal goes positive at an instant, the X1 terminal will also be positive at an instant. Okay, so have a read through those, and the most important part, though, is when we get next time, we'll head into doing something, we'll look a little bit more detail at examples here where we take a complete equivalent circuit and we shift everything, or real circuit rather, we shift everything to the primary side, get rid of the transformer completely, and then we analyze for voltages and currents. And then at the end, we can use that principles of, a voltage here will be A times what the voltage would have been if you were measuring it on the secondary side. That kind of thing, because of that shifting, impedance shifting principles that we discussed. So we'll dip into that again next time. I would suggest having a read through all of this stuff up until, try and even read through this voltage regulation, but we can talk about it together, but try and read through there. And I even suggest reading through the open circuit and short circuit tests and measuring these impedances. So if at all possible, do yourself a favor and read up to the end of page 214 here. Don't worry about this per unit method. So try and read up to the end of 1014. Then we can go quite quickly through these tests as to how you can find what is the resistance and leakage reactance on the primary and secondary side, or at least group them together into one big number and all those kind of things. So yeah, I'll read up to the end of page 214 and then we can I mean, just give it at least a cursory reading, see what you can glean from it. And again, I'll try and highlight the important parts of this. The test, putting power meters and parent power meters on primary and secondary side under certain conditions to measure these parameters, that's quite useful. Once we've got those parameters, we can put them into equivalent circuit, and then we can see what happens when we put a real load in the circuit. Okay.
Do the assignments come out sooner or later? It's easier to sort of work through the assignments as you're reading going through it all, or?
Yeah, I've got the assignment ready for transformers already.
Just so it's backtracking.
Yeah. Give me a day or two for a couple of tweaks, but pretty much that one is ready to roll. So, okay, so you reckon if you got the assignment in hand, it'll make it easier when you start going through all of these things?
Well, if you read all the questions, then you sort of know what to pick up most of. We'll watch these videos.
True. Okay. Fair point. So I'll get that out then as soon as possible so that you can actually know what you're looking for when you start reading through and look at the videos. Yeah.
Yeah, that'd be awesome. Thanks.
Okay, I'll do that. Of course, looking at it before you've even had a look at all at the videos, or you might wonder what the heck it's all on about. So it should come together when you see both.
Yeah, that's right. I'm like that with anything anyway, so it's all good.
Okay, you scare yourself a little bit when you see the assignment questions, and then relax a little bit when you start finding the answers.
That's right, yeah.
Okay, cool. All right, now I'll send that out as soon as I can. And yeah, that should help. Okay, cool.
Cool. Thank you.
Thank you.
Otherwise, good luck with finishing assignment 1, and yeah, try to get it out the way so you can do some reading of this.
Can you remind us of the due date?
I wish I could. 28th, was it?
Yeah, I think that sounds about right. Next
so
next
I said it wouldn't be the Monday, it would be the Tuesday.
That's right. Yep, gotcha.
Have you guys got other subjects that you've got during the week in the evenings?
Not at the moment.
And you, Cameron?
Oh no, not too much else. Yeah, this is pretty much it. But it's sort of definitely been taking up
At a time.
a bit of time.
You'll be a better person afterwards.
Yeah, that's right. That's right.
Or a better engineer at least, than about a better person.
Yeah.
You might be a frustrated one.
I just had a question on the shunt generators.
Yeah.
You know how you do the volt drop on the series resistor?
Yep.
When you go to do the motor version, and no, the long shunt and the series resistors on the other side,
Yep.
between the armature and the shunt resistor, do you take that when you're working out what the voltage or the EMF you'll be generating, do you have to take into that account that voltage drop across the series resistor?
Yes.
I'm just stuck. I'm getting a bit confused with my question now. Actually,
Yeah. Let me try and find it as well. If I
I think it was 7.
If I go to the, should I call it up quickly?
Yep.
I think I'll just stop the share here. No, I'll just stop the recording rather.
Yep.
That doesn't matter.
Yeah,
Electrical machines. This one, which one was it here? Okay, this one might not be the right version, but anyway, let's just see. I think I did the other one on campus. This was first semester one, actually. Okay, which one are you looking at?
7.
So this one had some different questions, but some of the same. Okay, yeah.
Yeah, I think it was maybe trying to work out the back EMF, I think.
Yeah.
maybe yeah. So your E equals your V minus your armature voltage minus
right.
your voltage drop of that resistor as well.
Was it the generator you're looking at or the motor?
Oh, I think it's the motor. Yeah, it's definitely. I'm just trying to think which one I was meaning there.
Because the generator one, it's similar.
I was working backwards from the generator on this one, pretty much.
Okay. Because if I just go to the generator one, excuse me, generator. Okay, so like for example, the generator, if you want 200 volts here,
yeah,
you've got to work quite hard to get it.
Yeah,
You've got to have, like, let's say it's whatever 220 volts over there, so that you can afford to drop maybe 10 volts across this thing because of current getting sucked through here.
Yeah.
That maybe gives you, let's say, 210 over here. Then you've got to afford to lose another 10 or something through this because current's getting sucked through there because of the load.
Yeah.
So that eventually you end up with 200. So yeah, the back EMF always ends up significantly higher than this voltage.
Yeah, and then
there's two steps of loss. One is through this guy, and the other is through this
that fella there.
Of course, this guy makes a bit of difference as well, because whatever the smaller he is, the more current's got to come out of the armature to feed him.
Oh, okay, yep.
So you get a bigger volt drop there. But once he's established, he's normally quite a high resistor, this guy.
Yep.
Very high resistance, lots and lots of thin windings. This guy here normally is fewer windings, fatter, carrying much higher current, because this guy carries all the load current. The series winding carries the full load current, whereas this guy only carries the current that's necessary to create the field that this thing's turning in.
Yeah, that makes sense, yeah.
Regardless of how much current you pull out of here, this current is not really affected much.
Yep.
This voltage is relatively fixed. It changes a little bit because of this little drop here, but pretty much it's closely almost fixed. So yeah, the other one,
it's just the EMF here. I would have thought you go V equals E equals your 240 minus your volt drop across your armature, and also minus your volt drop across that series resistor.
That's right. So if you want, they're both the same current. So if you want, you can. An option is that you just group them together into one R variable. Just call it R total or something.
Oh, okay. Yeah. No, that's cool.
Or call it whatever you want to call it. Just you obviously don't want to group this one with it.
No, that's just got a wee bit of current.
But because that's in the parallel. But these two, you can group them together. Or if you want, you can say there's a voltage drop here, IR across this one, and the voltage drop across there, IR across that one. But if you add those two, it'll be the same as if you took this one current and multiplied it by the sum of those two resistors, which is your series combination equivalent resistance anyway. So yes, they both cause a drop. So arrows wise, there'd be a positive arrow going upwards here, and what's happening here? The current's going through this way. Yeah, there's another positive arrow upwards this way as well. So yeah, that 240 would have 240 minus this minus that will leave me with
EMF.
Yeah, 240 minus this drop minus that drop will leave you with EMF. Yeah.
Yep.
This one's a bit of a challenge because it's perhaps slightly more complicated than the other ones, because I've got a combination of
your Webers, your milli Webers.
Yeah. So the important thing here is that for each ampere of current that flows in the series winding, so it's only the amps that run in the series windings here which cause an extra bit of flux to be produced.
Oh, yeah.
Whereas this flux is always produced because this guy permanently sees 240 volts.
Yep.
He's always producing his 12 milliwebers. But this guy, depending on how many amps get sucked through here, which depends on your torque here, depending how many amps get sucked through here, extra magnetism gets produced in this winding. Each amp that gets sucked through here, you get an extra 3 milliwebers. So you've got to take the effect of both of those fluxes together. They need to add effectively.
Okay.
That has an effect on, there's a formula for relating flux
speed,
pole, and the number of, the speed and the number of parallel paths and the number of pole pairs and all that stuff.
Yep.
You can jump into that formula and you can throw the numbers in there and see what happens.
Yep. Cool. Thank you.
Okay.
Perfect.
Cool. Perfect. Yeah, look, this DC sections is a fair chunk in the final exam.
Yep. Okay.
So, and these questions are all similar level to the exam questions. So, if you've got these ones worked out in your mind, there's a good, 20, 30, 25% of the paper.
Ooh.
So it's a good chunk. There's only DC machine section, there's a transformer section, there's induction motors and synchronous machines. It's those 4 main sections. And
so not much work at all.
No. But this DC machines is a good quarter at least.
Okay. Yeah.
Of the whole. So it's a big chunk. And it's the kind of stuff that I think once you've got your mind around it, if you see whatever question you see, you should be able to interpret. So it should make it fairly easy when you get to the exam. So keep pushing.
Do you think the exam will be after the block course, like our other courses have been?
So the plan is the exam will be. The plan is it's the first week of the exams. I think I did give you the dates in the Moodle site in the module forum. In the module guide and in the assessment block there. I think I do show it there on the Moodle site as well. Forget the dates, but it's the first week of the exam period.
Cool.
And the block course will be the Wednesday, Thursday, and Friday. And we should be able to finish all the prac stuff that we'll be doing then on hopefully not that deep into the Thursday afternoon, so we can have some time on Thursday afternoon and definitely Friday morning to do some revision for the exam on the Friday afternoon.
Sounds like a plan.
But Ben, I'm just thinking about that second block course, the time for that exam we can probably choose. Normally the exams are 9 o'clock in the morning or they're 1 o'clock in the afternoon. Now 1 o'clock till 4 o'clock would make you late for if you had that 3:50 flight.
I'd say we'd stay up there, it'll be our last paper, is it?
Yeah, no, we'll stay up and go home on the Saturday morning.
Okay.
Have to have a few beers to celebrate.
Yeah.
So,
I think we could do with the extra revision on the Friday morning. So
I'm not too worried, and I could arrange things with the invigilators that we have R1 shifted a little bit earlier if you want to, but then you do cut down a little bit of sort of time for revision and chilling out for an hour or so before you start the exam. So we can look at it, but
I'm not too worried for that one.
Okay.
Just for the first block course.
Just for the first one. Okay, cool. All right. So probably we'll stick them with the 1 till 4, and if you have to spend one more night, then you'll live through it, I guess. Partying.
Bosque Bay.
Yeah, should be good.
Okay,
Sounds
cool.
good.
All right, thanks guys. Thanks for listening, and I hope it's helpful. And I'll get the assignment out when I can.
Excellent.
Cool.
Cheers.
By the way, the assignment will have in it stuff on 3-phase transformers as well, which obviously won't make much sense yet, but I'll give it to you anyway.
Yep.
Okay.
Cool. Cheers.
Sweet.
Cheers. Thank you. See you later. See you, Ben.
See you, mate.
Behave yourselves.
Will do.